This is Physical Science 2, Chapter 26, Part 1 on Stars and Galaxies. In this portion of the video lecture, we will be discussing the astronomer's tools of the trade, known as the telescope. Before the invention of the telescope, of course, we have ancient peoples using the ever-present tool of the human eyeballs to make observations of stars at night. And due to ancient peoples having a very heavy oral tradition, a story type of tradition to their culture, a lot of different cultures would come up with stories to go along with what they saw in the sky. And they kind of developed this idea of a constellation or a pattern or a group of stars that represents something to that culture. Most of the constellations, generally the stars are completely unrelated. They just happen to look close together from our point of view from Earth. We have there on the right side the Big Dipper, which of course is part of the constellation Polaris, the Big Bear. Another famous constellation is Orion, the Hunter. He's usually present in the northern hemisphere during the winter time. He's very easily identified by his 3 stars on Orion's belt and his shield. But eventually we needed more information as to what and why these stars were placed in the sky. The reason why constellations held for so many years is because they are visible with the unaided eye. Once we get very early telescopes, we can see a little bit further out into space. We can't see necessarily individual stars, other than, of course, our own sun. But telescopes were a way to get more information from the sky than just what we could see with our eyes. So optical telescopes are those types of telescopes that study objects in visible light. Visible light is part of the electromagnetic spectrum. We see a very small portion of the different types of waves that are present. So the visible part of the light spectrum is what optical telescopes study. You can figure out how strong your telescope is or how much it can magnify. Remember, magnification is something that makes an object larger. So the magnifying power, you can take the objective focal length, meaning the length that it takes the objective lens to focus, and you divide that by the eyepiece focal length, and you can get the strength of your telescope. A type of optical telescope, when you think of a telescope, you probably normally think of what we call a refracting telescope. A refracting telescope uses lenses, and they are convex, which means they kind of bubble out from the sides. So light passes through the objective lens, it will turn to a focus point, and then the eyepiece is the part of the telescope that magnifies the image. A reflecting telescope is another type of common optical telescope. A reflecting telescope uses a mirror as an objective lens. So just like a mirror gives you your reflection, a mirror can also make light focus to a finer point. So light passes through an open end of a reflecting telescope, and it strikes a concave mirror at its base. So a concave mirror dips in the middle, and it can focus light with more resolution or more detail or clarity. So there's 2 things when we have to keep in mind when discussing telescopes. Not only magnification is important, making things appear larger in our view is important, but also the resolution or the detail, the clarity of what we are magnifying is important as well. Because if you take a big fuzzy blob and you magnify that and make it even larger, it's only going to be a larger fuzzy blob. It's not going to get any more detailed. So both magnification and resolution are very important for optical telescopes. Nowadays, of course, with technology, we can have computers help us correct for changes in temperature in the atmosphere, changes for correction in the mirror, and general bad viewing conditions. We call these active optics. Active optics are generally hooked up to conservatory telescopes, so they can take into account that because these telescopes are Earth-based, we have to get through all of the layers of our atmosphere before we can view outer space. And so active optics help make those changes. Adaptive optics are another type of technology that have been added to telescopes. Lasers probe the atmosphere and they relay information to a computer. Now the image that you see here on the right side would be an image as you would see through a normal telescope without the help of active or adaptive optics. On the left side is the same image that has been cleaned up essentially due to bad viewing conditions. Now astronomers, when they observe stars in the sky, we use a general indication of light and associate that with heat. So generally, the brighter a star is, the hotter it is. Now, you would get some misinformation if you only used the right-hand side of this diagram. This star looks very large and very hot. However, once we get some of that cleaned up, we can see that the star isn't exactly as large as we had thought, and it's a lot cooler at its core. Another type of telescope is a radio telescope. These are very large telescopes. They collect and amplify radio waves. Radio waves have very long wavelengths, so you have to have a large dish-type antenna required to collect such long waves. The Hubble Space Telescope is probably one of the most famous space-based telescopes that we have. The advantage of the Hubble Space Telescope is that it is already up and out of all of our layers of atmosphere, so we don't have to use as much active and adaptive optics with Hubble. Now, Hubble is a reflecting telescope, so it does use a mirror. The Hubble Space Telescope measures distances in light years. So a light year is the distance that light travels in 1 year. Keep in mind that a light year is not a measurement of time, it is a measurement of distance. So active and adaptive optics for the Hubble Space Telescope can see and use this more to our advantage to see deeper and deeper into space. Around the year 2018, this is still up for grabs for the date of the launch, but the newest of the space-based telescopes is the James Webb Space Telescope. It is much larger than Hubble, and it will be able to see much further due to the arrangement of its mirror. And you can see here in comparison, the Hubble primary mirror is one continuous mirror, whereas the James Webb telescope has kind of a honeycomb shape, and you can individually position each one of those mirrors to get the highest resolution possible. A spectroscope is a very special type of telescope that astronomers use. Spectroscope gives a wavelength breakdown of every single star, and it uses a prism to do that. So a prism breaks the light into identifying wavelengths. So a spectroscope is used to almost identify a star. It can give us a general chemical composition of the star, what types of gases are found in it. It can also give us a surface temperature, and it can detect very slight movement of stars. So a lot of times we use spectroscopes to view very deep field stars to notice their motion. This has been Physical Science 2, Chapter 26, Part 1 on stars and galaxies.